So hello, good morning, good afternoon, and good evening. Welcome to the MOF 2024 webinar series. Uh, Before today's webinar, which will be the sixth of the whole webinar series, I'm going to introduce the MOF conference to you. So this is a brief history of the MOF conference. The MOF conference focuses on the recent advancements in metal organic frameworks, MOFs for short, covalent organic frameworks, COFs, and other porous materials. And this conference is the most well-established conference in the field, with close to 2 decades of history. It started in 2008 in Augsburg in Germany, and then Marseille in France, Edinburgh in UK, Kobe in Japan. That is the first in Asia, and Long Beach in USA, Auckland, New Zealand. 2020 was online due to the COVID. 2022 was held in Dresden, Germany. And this year, we are very glad to bring the conference back to Asia again in Singapore. So the MOF 2024 will be held in Singapore. Singapore is a very exciting place to visit. Here you can enjoy both the East and West cultures. You can enjoy both food and the gardens and the beautiful sight. Although Singapore has often been blamed for the hot weather, but trust me, during the conference period, which is the middle of July, you'll be surprised to see that Singapore actually will be cooler than most part of the world. The MOF 2024 conference is held by Material Research Society of Singapore and co-hosted by National University of Singapore, the Nanyang Technological University, the Singapore University of Technology and Design, and Agents for Science, Technology, and Research of Singapore. So we have 5 themes and topics. They are materials, fundamental phenomena and properties, synthetic methods, characterizations and applications, and industrial integration. So you will enjoy a full 1 week of the conference. The conference will start with a 2-day pre-conference, July the 13th and 14th. This 2-day pre-conference will be held at NUS. So we will invite the people at their early career stage, and we will also organize some materials characterization workshop. So you can learn new knowledge. Also, you can start to build your network. So the main conference will start on July the 15th, and then it will end on July the 19th, which is a Friday. So we have invited the pioneer researchers in this field, Professor Suzumi Kitagawa from Kyoto University and Professor Omiyagi from UC Berkeley as our special speakers. And they will be delivering plenary talks during the pre-conference and during the gala dinner, respectively. And this conference targets at about 1,000 participants. So we have planned for 8 plenary talks, 47 keynote presentations, 79 invited presentations, 163 oral presentations, and 700 posters. So on top of the main conference, we have the pre-conference, and we have also organized the editors forum and industry forum. And we also have gala dinner and a social visit. All of this is to ensure that you will enjoy a rich conference experience during your stay at Singapore. So in the editors forum, we have invited editors from multiple publishers, such as ACS, the Chinese Chemical Society, the Royal Society of Chemistry, and Elsevier. And you can see that all the flagship journals in terms of the chemistry and the material science can be found here. So it's a great opportunity to discuss with the editors about your next exciting finding. Besides the editors forum, we have also organized industry forum. So here you can see the active players in industry with MOF suppliers, MOF users, and we hope to close the loop so that the world can witness not only the fundamental, but the exciting application of those materials. So far, I am glad to let you know that we have received 1,040 abstracts, and they come from everywhere in the world, the majority comes from China, and we have a lot of submissions from Germany, USA, UK, India, and Japan. And we covered mainly 5 themes, and among the 5, the theme 1, materials, and theme 5, applications and industrial integration, are the most popular themes that we have received the most abstract submission. So it's very clear to see the joint effort between fundamental research and application in the MOF 2024. So here are some important dates. We have already sent out our decision on your abstract submission. So right now, if you have submitted an abstract to MOF 2024, you should have heard from the committee, the decision. I have to say that we have received way more requests for oral presentations than we can accommodate. So unfortunately, we have to convert many oral presentation requests to posters. And the oral presentation acceptance rate for MOF 2024 is only about 30%. And that would make MOF 2024 one of the most competitive conference. But having said those, we hope that our exciting program will not discourage you from attending. So we warmly welcome you to attend the conference. And the early bird registration deadline is 15 April. So if you want to enjoy the discount, please register as soon as possible. In addition, we have a limited slot in some of the program, so the early the better. So please join us. If you want to know more about the conference, feel free to visit our website. You can also follow us through our social media platforms, the X or the WeChat. And before starting today's webinar, please allow me to introduce our next webinar, the 7th webinar, with the title Microporous Polymers and Framework Membranes for Electrochemical Energy Storage, from Professor Chile Song of the UK. It will be held in May the 7th, 2024. So stay tuned. Now let me introduce our speaker for today's webinar. Today's webinar will be given by Dr. Nobuhiro Yanai. He is an associate professor in the Department of Applied Chemistry and Kyushu University, Japan. He earned his PhD from Kyoto University in 2011 under Professor Suzumu Kitagawa, who is a special speaker of MOF 2024, and Professor Takashi Uemura, who is another invited speaker of MOF 2024, on guest properties in metal organic frameworks. He was a postdoc research with Prof. Steve Granick at the University of Illinois at Urbana-Champaign, experiencing colloid and soft matter sciences. So he joined the Kyushu University in 2012. He is currently leading a group that creates photo-functional materials for photo upconversion, dynamic nuclear polarization, and quantum sensing. So he received several awards, including the Wiley Young Researcher Award, the Asian and Oceanian Photochemistry Association Prize for Young Scientists, and Award for Young Chemists, Chemical Society of Japan. So without any further ado, please join me to welcome our speaker, Professor Nobuhiro Yanai.
Okay, thank you very much, Professor Zhao, for your kind introduction. So this is Nobu Yanai from Kyushu University, Japan. So please call me Nobu. So this is my really great pleasure to talk here in this webinar series, and I really appreciate Professor Zhao and all the committee members of this MOF 2024 for such a perfect organization even before the conference. I'm really looking forward to see you all and talk to you in the in-person meeting in Singapore. Okay, so today I'm gonna share some of our recent works on the some of our initial trials to the quantum sensing in the MOFs. So our group are quite interested in the photoexcited state of the molecules. So we make the molecular-based materials, of course, including MOFs, and we create the optical and spin functions. And eventually, we want to develop the new interdisciplinary fields based on our materials and functions. So among the different various functions, we have been focusing on these topics shown here, like the top two ones related to the energy degree of freedom of the photoexcited states. So it's about the wavelength conversion, photon up conversion, and also singlet fission. But recently we put more efforts on the spin degree of freedom of the molecules, like hyperpolarization to increase the NMR and MRI sensitivity, and also the quantum sensing. So since this is the MOF conference, so today I chose the topic of the quantum sensing that's the most relevant to the MOF chemistry. Okay, so now we are living in the second quantum revolution. It's all about application of the quantum mechanics. So it's also called as quantum information science, QAS, that includes the quantum computing. Of course, this is the major driving force of this QAS, but not only quantum computing, but also the quantum communication and quantum sensing are very important quantum technologies. So as a chemist, and material chemist, MOF chemist, we ask ourselves, okay, so what we can do, how we can contribute to this coming or ongoing quantum era. And then we found the quantum sensing can be a very good starting point because the target of quantum sensing can be like physical parameters like temperature or magnetic field and so on, but it can be also chemical parameters like molecules, metabolites, proteins, biomolecules. So such kind of molecules, molecular targets, we feel the more familiar, and we feel that we can do something on that. Okay, but I should say that this is using the MOFs for the quantum sensing. It's very in the beginning stage. But I want to share you some of the very initial results. But before going to the detail, I want to mention about a little bit of background of this quantum sensing. So here's the definition of the quantum sensing. So it's the most widely accepted definition, and you should satisfy at least one of these three definitions. So first one, the broadest one, is the use of quantized energy levels. So any quantized energy level is fine, like electronic, magnetic, vibrational, and so on. So, but this is very broad. So, if you see some change of the color of the material, or you see some, change of the photoluminescence or fluorescence, it's already, in the broadest sense, it's quantum sensing. But usually, it's not called as quantum sensing. So, perhaps the most common way to define quantum sensing is if you use the quantum coherence. It's a superposition state, like a superposition of 0 and 1 state. So it's also exemplified as a Schrödinger's cat, alive and dead state. So using such a coherent state, because coherent state is very sensitive, it's very fragile. So it's not very easy to keep such coherent state for a very, very long time. Of course, but it's very important for quantum computing, but it's not easy. But you can take advantage of such, fragility or sensitivity. Actually, it becomes advantage if you want to use it for the quantum sensing. So that's why the quantum sensing have a potential to give you the very, very high sensitivity. And actually, that sensitivity is directly related to the coherence time or spin-spin relaxation time T2. So that's why the coherence time is desired to be long, like microsecond time scale. And third definition, that's maybe the most advanced definition, is the use of quantum entanglement that used entangled qubits. That's very limited examples, but still there's some. It's because entanglement of the qubits can further enhance the sensitivity. Okay, so perhaps you feel that the quantum sensing is very, very special system that you may find it only very, sophisticated sensors, but actually you can find very the quantum sensing even around your life. For example, perhaps the most important and the famous example is this bird called European robin. So this very cute small songbirds may travel amazingly long distance from, for example, from the north part of Europe to the even to the Africa. So in summer, they want to stay in north because the Africa is too hot, but in winter, it becomes cold, so they travel all the way to the south part of Europe or Africa. So how they know the directions? Of course, human can know the direction in many ways, but the bird doesn't have the tool. So, but the birds can know the directions, and they can know the direction. They know which direction they should fly, and they know they can fly in such a very, very long distance, very precisely. Amazing. And there are many, there are several like the mechanisms proposed to explain this amazing, long distance navigation behavior. And one of the most promising mechanism or most probable mechanism is the chemical magnet reception, or you can say it's a chemical compass in birds. So birds, this hypothesis expect that the birds have some protein. It's called cryptochrome. When cryptochrome absorbs the light, it forms the photo-induced charge separation or electron transfer to make the radical pair, radical cation and ion. And these radical pair, it's pair. So each radical have one electron. So radical pair have two electrons. And these two electrons are coupled. And it form either the singlet or triplet state. So singlet or triplet state. And when this two radical, the distance of two radical becomes a bit far, the exchange couple interaction between the radical becomes a bit kind of weak. And that makes the energy difference between this singlet and triplet very close. So what happens is that, so one of the triplet sublevel, T0, and the singlet becomes the very close, and they start to mix, and they make the quantum coherent state. And actually, hyperfine coupling interaction mix these two singlet and triplet states. And importantly, by using such weak interactions, actually, that hyperfine coupling interaction can be dependent on, or can be in the similar energy scale of the geomagnetic field. So you can feel the geomagnetic, so this system can feel the geomagnetic field, and then they change the product of chemical reaction. So then eventually birds can see the direction. It's still hypothesized, but it's there are many experimental evidence is accumulated. Still, everything, not everything is understood, but it's still very strong hypothesis. But this is very inspiring, and it's very interesting. So you can produce the quantum coherence in such a noisy, messy situation, and in the room temperature in biological system, and you can actually use it as a compass. But of course, human has a compass, so we don't need to, do the same thing, and we cannot use the cryptochrome because it's too much fragile, and we cannot make a lot of amounts. So, but so that people make the artificial or molecular qubits. Some are directly inspired by the radical pair of the chemical compass. But some are very different, like this type of radical pair systems, or the metal complex, or some metal complex radical conjugates were developed. So these are the beautiful examples of the molecular qubits, and there are so many nice examples. But the question here is, okay, so you have the nice qubit, you can synthesize it, But how to make it interact with your target, especially if you want to use it for the chemical sensing, you need to have interactions between these qubits and your target analyte. So for that, MOFs, I think most of you are interested in, is very promising for these applications. Gives a very powerful, can be a very powerful platform for the quantum sensing, because you can install such a molecular qubits in MOF with very good precision. And also, of course, it's has an open pore, so analyte molecules can go in and interact with the qubit. So actually, there's this is the very nice picture from the review by Dana Friedman. So if you're interested, I suggest you to check it. And also, there are some pioneering works in this field. For example, Kudeva and coworkers used the copper zinc mixed metal system of HCAST1, and they used the copper as a paramagnetic qubits for the quantum sensing of some gas molecule, in this case, butane. So they observed some hyperfine or dipole-dipole interaction between this electron spin and nuclear spin protons of the butane. Actually, in this case, at cryogenic temperature. And then Sun and Dinker and Raj and co-workers reported a very nice example using the radical qubits. This radical stays in this region of the MOF. And then they produce the radicals, and they use this radical as a qubit for the quantum sensing of lithium ion. So they observe the hyperfine copper interaction between the lithium and radical, and they could detect they could quantify the amount of the lithium. Okay, so but as you see, these are the very beautiful examples, but the number of examples is quite limited. It's quite, I should emphasize, this is the beginning of this new direction using the MOF in the quantum sensing. But as you see, the target analysis is quite limited, like butane or lithium. And I should mention that these examples can detect the type of nuclear, like you guessed have a proton or you guessed have a lithium, because these have nuclear spins. But you cannot distinguish if the molecule you guessed have a similar nuclear spins. For example, you cannot distinguish benzene or toluene because most of them have copper and proton. So obviously, we need more variety of the quantum sensors that can detect the that can distinguish the different gas species. So we need good designs for that. And also, I should emphasize that these systems still have a limitation of the sensitivity. So there's some reasons, but one of the reasons is that they use the thermal equilibrium state of the spins. So actually, they use both of these systems. Previous example used the EPL. We also use the EPL electron paramagnetic resonance to do the quantum sensing. And the sensitivity of EPL is proportional to this electron spin polarization that is defined by the difference of the up and down spins over the total number of spins. So in the normal condition, like expand EPL, 0.34 Tesla at room temperature, this polarization is only like 0.08%. So most of the spins are canceled out. You cannot see it. So you see only remaining 0.08% of the spins. So there's a method well developed in the magnetic resonance community. It's called as a dynamic electron polarization, so that you can make this difference of the number between the up and down spins bigger, and then you can enhance the sensitivity. But how? Okay, there are several methods, but one of the very easy way and our favorite way is using this large non-equilibrium polarization of photoexcited state. Especially in this case, I show the example of the photoexcited triple state. So when you shine the light of the chromophore such as pentacene, it excited to the S1 state and it undergoes the intersystem crossing to the triple state. But this intersystem crossing can be sub-level selective. So you can selectively populate one of the three sublevels of the triple state. So in case of pentasene, you can have the very large polarization over 70%. So if you compare with the thermal equilibrium 0.08%, it's surprisingly large. So just shining the light, you can make such a high polarization, you can increase the sensitivity. And also I should emphasize that you can even detect this polarization not only by EPR or ESR, by directly observing the absorption or emission of the microwave, but also you can detect by photoluminescence. So that can give you even much higher sensitivity, because EPL, you need a very large ensemble of the spins, but the photoluminescence, you can even detect from single molecule. So this is still very in future task, but I want to emphasize that this using the photoexcited state as a qubit have a very promising in terms of the increase of sensitivity. But maybe you're not familiar with the characterization of the photoexcited state by EPL, so I should give a few notes on it. So you need the so-called transient EPL. That is you need do the EPL measurement at the fixed magnetic field under the continuous microwave irradiation. You shine the pulse laser, and then you monitor the decay of the EPL signal. So for example, you set a 350 millitesla, and then shine the light and see the EPL curve, the decay. And then you change the magnetic field, and you measure, change, and measure, and eventually you get this two-dimensional information between the magnetic field and the time. And this is the triplet. And if you take the slice at a certain time, for example, right after the right irradiation, you see this type of the spectrum. This is typical for the triplet state. It's a bit complex spectrum. It has a lot of information. For example, by checking the width of this spectrum, you get information about the energy level of the three sublevels. It's called as a zero field splitting. And also, you can know the direction of the molecule against the magnetic field, so that depending on the direction of the molecule against the magnetic field, you see the EPL transition at a different position. For example, if the molecule is X-oriented, you see the absorption emission here, and if Y-oriented, here, Z-oriented, here. So by simulating the so-called powder pattern that contains all the oriented information, all the orientations of the molecules, so that you can get the relative population of these three sublevels, that is the polarization. And also, I should mention that there are two very important time constant, the acquisition times of the electron spins. One is a spin lattice acquisition time. That is the time takes from the polarized state, right after the photoirradiation, you can make the polarized state that have the population of the specific sublevel, and then it takes the time of T1 to relax to the thermal equilibrium state. So you can use time dissolved EPL and more precisely pulse EPL to determine that. And also, another very important parameter is coherence time that already mentioned. That's that can keep the time to keep the quantum coherence, and that is you can measure determined by the Hahn echo pulse sequence of the EPL. So right after the right irradiation, you initialize and you have these initial populations. That is in Bloch sphere in the rotating frame. It has a magnetization against to the z-axis, and then after that you shine the pulse of the microwave. For example, in the case this half pi pulse to make the change direction to the XY plane, and then this the spins actually dephase, but actually if you again shine the pi pulse, you can refocus it and then get the echo signal. And by changing the time between these pulses, you can get the coherence time, because if you wait too long, the coherence is lost. Okay, so if you're interested, you can check the maybe Wikipedia to see more nice movie to understand better. Okay, but anyway, we use these APL techniques to see the coherence and do the quantum sensing. Okay, so let me move to some examples. So here we use photo-excited triplet state as a qubit, and we take the responsive flexible MOF. Okay, we use the triplet because we can make the highly polarized state, and eventually we can we use the EPL, but eventually we can also use the optical detection. And then we use the responsive flexible MOF. If you're MOF chemistry, you're very familiar. There are so many flexible MOFs, and the flexible MOF can change the shape of the pores. So when we accommodate the gas, it changes the pore. So we expect it to do some, if to the effect of this quantum coherence of our qubit. This is a collaboration with Dr. Nakamura and Asada at IMS. And this and done by Akio in a group. So this is the choice of our MOF, and the very famous, one of the most famous flexible MOF, mu-53. And when it absorbed the gas, different gas species, it shows the change of the volume, and beautifully MOF developed by Ferrer group. And then we introduced our favorite chromophore qubit, DAT, diazotetracene. This has a very nice advantage compared with the typical triplet molecule pentacene, because DAT have better solubility in the organic solvent, and also it has a better air stability. So we can easily introduce this DAT into the MOF pore by just soaking the MOF powder in the solution of the DAT. And by changing the concentration of DAT in solution, we can control the concentration of DAT, and if we keep the low concentration here, 0.87% weight%, because we don't want to have interaction, or we don't want to have aggregation of these qubits. Okay, but still, this amount of DAT is very small, so we have a lot of pores remaining, so we can introduce these gas molecules. And here is the results of the pulse EPL. So we shine the laser light, and we apply the half pi pulse and pi pulse and get echo signal. And by changing this tau, we got this decay of the echo intensity. So empty means the only DAT is included, no other gas molecules. It gives this decay of the coherence with the T2 coherence time, or spin transition time of 0.1 microsecond. And interestingly, when we introduce some other gas molecules, it gives the elongation, it gives the longer T2 with some gas, and sometimes it gives over 1 microsecond. It's very long at room temperature. So, and when we plot the T2 against the volume of this unit cell of the mu-53, we saw some trend, not very simple, but we saw some trend. And also, I should note that with some gas, the T2 becomes longer than the empty situation. This is kind of interesting, because usually these molecules have a nucleus spin, so it should be it should decrease T2, but now it's increased. So so we want to understand this behavior. Before that, I should explain what kind of processes can affect the T2. I borrowed this figure from this nice review. So there are several processes affect the coherence time. For example, electron-electron interaction, but if you dilute, you can avoid it. And the T1, spin-dust dilation, but if it's long enough, it doesn't control the T2. And the other parameter you need to think, for example, the rotation of the functional group, and also the nucleus spin diffusion. So nucleus spin diffusion exists always all the time, because if you have like molecules having the protons surrounding the qubit, even without the molecular diffusion, like nuclear spins can diffuse by the flip-flop, even in the solid state. So actually, if you have the protons or some fluorine and nucleus, nitrogen nuclear spins, you have a lot of spins. So actually, it can give some relaxation to the coherence. So that's why I was saying that it's a bit surprising to see the enhancement of the coherence time and in many gas molecules. So these nuclear spins cannot explain. So what else? So actually, also mentioned in this review that the molecular liberation, the motion, wiggling or stretching of entire molecule can also affect the T2. So we are thinking this can play an important role, but to understand the possible reasons to affect T2, we did our best to understand. So first, we measure the absorption spectrum of the DAT. So we confirm there are no aggregation of the DAT because we don't see such a very big shift like a neat solid of the DAT. And there are some small shifts, but when we check the when we check the relationship between T2 and directly constant of solvent, but there are no obvious trend. And also, we check the EPL spectrum. Well, first of all, there are no change in the zero field splitting parameters. So, and also, there are very small change in the relative polarization. That means that there are no significant interactions between the triplet of the qubit and the gas molecules. I don't say no interactions, but that may not be the major reason. And then when we check the amount of the gas by TGA curve, and we calculate the gas occupied volume, that's the kind of local density surrounding our triplet qubit. We saw some trend, positive trend, like T2 becomes longer with the higher gas occupied volume. So that's suggesting us that with the denser situation, perhaps this triplet becomes less mobile, and then the coherence is more preserved. So to support that idea, we collaborated with Jiang and Yu at Nagoya University and carry out MD simulations. So in the empty situations, the AT can actually move, still diffuse, change the orientation and diffuse in nanosecond time scale. But in the presence of some gas like benzoquinone, such a motion is quite suppressed. So indeed, this DAT mobility is quite suppressed. And also when we measure the coherence time by lowering the temperature, at 50 K, we observe the much longer coherence time, and that becomes close to the coherence time of DAT in dense molecular crystal of partalphenyl. So this also supposes that at least partially this mobility should be suppressed at lower temperature, and it becomes very close to such a very, very dense situation, even in the MOF empty situation, and that enhances the coherence time. So there should be several parameters, but at this moment we consider that the major source or major reason of this enhanced coherence time is the mobility. So by introducing the gas, we increases the density, and that increase the T2, and T2 becomes very long at room temperature. But you may wonder, okay, is this a quantum sensing? Are you sensing quantum sensing of the gas molecule? Well, it's a kind of tricky because maybe we are seeing the mobility, not directly the molecule, it's the target analyte itself. But I should ask you to recall the definition of the quantum sensing. So quantum sensing definition includes the use of quantum coherence. We do use the quantum coherence to see the different chemical species. So our system should also be classified as one type of the quantum sensing. Okay, so the previous example used the direct dipole-dipole hyperfine coupling interaction between the qubit and the nuclear spins. Of course, this is kind of quantum sensing, but in our system, maybe I can say that it's kind of indirect detection. So maybe there are no very strong direct interaction between the electron spins and our target analytes, but target analytes change the MOF structure and the mobility change, and eventually this coherence changed. So here, the MOF works on molecular recognition, and the qubit is the reporter of such recognition event. And if you're a MOF chemist, you know many examples of the selective, accommodation of molecular recognition using very different type of the MOF. So we can utilize such a very huge variety of the molecular recognition for this quantum sensing if you put your qubit into the pore. Okay, so and then in the rest of time, let me show you two more examples about the different way of making the qubits in the MOF. So I already explained that qubit can be very interesting and powerful way of making qubit. But actually, to be honest, by chance, we found that when we accumulate our chromophore in the very high density, we observed the charge separation and produce the radicals. And this radical actually can be also very powerful qubit because we can transfer the polarization from the qubit to this radical, but through the charge separation process. And this radical can also have a very long relaxation time. So this is the MOF we made. So now we again use the DAT, but now we attach the bipyridyl group to this DAT and I made a MOF with the coligand. And within the MOF, we didn't see the strong pi-pi stacking, very close distance between the DAT, but rather we observed the close distance between this DAT and coligand biphenyl. They form the pi-pi stacking. Okay, when we measure the transient EPL of only ligand dispersed in 40-man matrix, we observe just a very typical qubit EPL signal. But when we measure MOF, in addition to this qubit signal, we observe this sharp radical signal in the middle. So we confirm this is the radical by nutation experiment by comparing the nutation frequency between qubit and radical. And this is actually the radical. And then it shows the emission. So obviously this is the polarized radical that keeps the polarization from the qubit. And interestingly, when we observe the time course of this EPL spectrum, how it changes over time, actually qubit signal decays quickly within microsecond, but the radical signal stays over 100 microseconds, very long, even room temperature. And when we see in the beginning, the qubit decays within that microsecond, and the radical emissive signal emerges in a similar time scale. So we think at least partially, this polarization of the qubit is transferred to the radical through the when they do the electron transfer, the photo-induced charge separation. And we determine this spin lattice acceleration T1e by the inversion recovery sequence of the pulse EPL. And we found this T1 is very long, like over 200 microseconds at room temperature in open MOF framework. So it can be very useful. And then this actually we consider that it's partially because this mobility of this DAT is suppressed by the forming the pi stacking with the coligand. And also we measure the T2 by applying Han echo half pi and pi pulse sequence. And again, we observe kind of long coherence time, nearly 1 microsecond at room temperature for this radical. And when we add some gas molecule like a paraffin, we observe some decrease of coherence time. So we add the noise, it decreased. So that it can be also useful for the quantum sensing of gas molecules. And we confirm the generality of our finding by changing the coligand, like changing from the biphenyl to the some tetracarboxy ligand and also terephthalate. So we again observe this emissive radical signal. And also we observed the long T1 and T2 for all these series of the MOFs. And we compare the T2, so the DAT MOF1, the original one was showed the longest T2, and we expect that at least partially this pi stacking helps to reduce the relaxation, because in other two MOFs they can still rotate, or at least there are no pi stacking. So the suppression of the mobility should help to increase the T2 coherence time. And my last example today is the how to make the spin entanglement in MOFs. As I mentioned, it's important to entangle more spins to increase the sensitivity of the quantum sensing. If you entangle triplet and radical, you can get the Coulter state having two spins. And if you entangle the two triplets, you can have the Coulter state with 4 electron spins. So that it's but the question is how to make such state in the MOF. And let me show you one example of the quintet state. So actually, there are very nice method to make the quintet state using the molecular systems called singlet fission. So singlet fission is a process that makes the two triplet photoexcited triplet state out of one photoexcited singlet state. For example, pentasene is the most famous representative example. So when pentasene aggregate, it shows the singlet fission to the ultrafast singlet fission to make the triplet state. And as a key intermediate of this singlet fission, there is a triplet pair state, and especially the quintet triplet pair state. So this has the 4 electron spins entangled, and also you can make the polarized state of this quintet state. So there is some advantage of using this quintet state. First of all, of course, they have the 4 electron spin entangled, so you can expect the higher sensitivity of quantum sensing. And also, this singlet fission can be reversible for some molecules. So that the singlet fission and reverse process is the triplet annihilation TTA at conversion. So this TTA can go back to the singlet, and it gives you the emission. So this reversible reaction can give you the optical readout. So you can even detect the optical signal to do the magnetic resonance, so-called optically detected magnetic resonance, or the MO you can do, so that you can expect even higher sensitivity. Okay, so it has the promising potential. And then I want to show you the very nice example of observation of the qubit, the quantum coherence of such a quintet state in the molecular crystals or the isolated dimers. But these are the nice observations, but I should mention that these are the low temperature, and there have been no example of room temperature observation, but we want to use it, quantum sensing at room temperature, so we want to achieve the quantum coherence at room temperature. So for that, we made the MOF based on the pentasene, and this, and also we made this carboxylate ligand and combine with zirconium ion and make the UIO type MOF. It has a very dense accumulated pentasene units. And when we do the transient absorption, ultrafast transient absorption spectroscopy, we observe the picosecond time scale emergence of the triplet. So that cannot be explained by intersystem crossing. That should be due to the singlet fission and to produce the first singlet TT triplet dimer state, because it's a spin preserved process. So it's very quick. And then it takes nanoseconds for the spin evolution to make the quintet TT triplet pair state that can be observed by the times of APL. And then we did the pulse EPL measurements to see the quantum coherence at room temperature. Fortunately, we could see the quintet quantum coherence at room temperature for the first time, and this coherence time was over 100 nanoseconds. So we wanted to understand why we could observe it. So we further carried out the nutation experiments of the pulse EPL, and by analyzing this nutation behavior, and this was analyzed by the Professor Kobori at Kobe University. They also measured the pulse EPL. So they observed some small change of the dihedral angle between 130 and 122 degrees between the Henderson units. So actually, such a suppressed motion exists. That is important we consider. So actually, this small motion helps in the first place to produce the quintet state out of singlet state. But if you have the too big motion, that motion should induce the relaxation. So you cannot see the quantum coherence at room temperature. So that you should have the motion, but the motion should be very small. So in the MOF, the pentasyn is very, very densely accumulated, so it cannot freely rotate. The motion is quite suppressed. So such a suppressed motion plays an important role in this formation of the quantum quintet, and also the maintenance of the quantum coherence even at room temperature. So finally, this is the conclusion. So I want to conclude that about what we have learned. So actually, we found in a series of different systems, the suppressing the mobility of the qubit is important to elongate the coherence time. Okay, so I'm not saying this is the new finding in terms of the magnetic resonance. So this EPL community is great. So they have the very in-depth understanding what affects the coherence time. And of course, the mobility of it had been known that the mobility of the molecule should be related to the coherence time. But in reality, in MOF, it's open framework. You have the qubit next to the open pore. So it's quite important how to design the molecule or materials with less mobility. We found that is a very important key parameter when we design the quantum sensor using the MOF. And also, we found it's interesting to use even the mobility. So if you change the mobility, you can change the coherence. So as I show you in the first example, it can be the additional parameter that you can tune. Actually, such kind of parameter did not exist in the conventional or previous examples of the quantum sensor like NV-centered diamond. It's embedded in the very rigid framework. But now we use the open framework. So mobility can be changed, can be tuned. That can be an interesting way of tuning the coherence and for the quantum coherence. So for the quantum sensing. So with that, I want to thank all my coworkers, like current group members, previous group members, and our wonderful collaborators and kind financial supports. And thank you very much for your kind attention.
Thank you, Nobu, for bringing us to the world of quantum. Okay, I have many, many questions, but I think I will start from the audience. So we have so far one question from the Q&A, Awasha. She's from my group, by the way. She's working on chemical senses. So very nice, interesting presentation, Prof. Yanai. Do you think that the guest-dependent coherence time can help to selectively identify components in a mixture of gases in the real-world environment? Also, can quantum sensing phenomena be used to sense any target analyte or any specific criteria molecular properties of the guest molecules need to be met?
Yeah, thank you very much. What a nice question. It's a very important question. So actually, so far now we are really in the stage of understanding. How first of all how we can design the material to have the enough long coherence time and how we can utilize it. So so far we only use the one simple type of the gas, and we didn't try the mixture. So of course it's a challenge, but I think that the key to distinguish the different gas molecules or the mixtures is that we need to have more variety of the quantum sensor. So that is one way I believe. So that if you have the variety, different type of the sensor like this, or even you can find many, there's so many MOFs, and also there's many qubits you can think of. So that by combination of them, you can make thousands or many, combination and the hybrid material. So that may give you each system can give you the different response, so that if you make more sensors, so that you can combination, and then you can eventually do the sensing of or distinguish the different gas, or even the of course this is the very optimistic thinking, but maybe mixture can be also distinguished. And the second way is like beautifully exemplified in the previous works. So they used hyperfine couple interaction, and one of the example distinguish between the lithium and sodium. So that because they have the different nuclear spins. So if you have the different nucleus, if your target mixture have different nuclear spins, you have also chance to use the such advanced EPL technique to distinguish the different gas molecules.
I see.
Yeah, and also any specific criteria. Okay, so in the if you want to use such a hyperfine couple interaction, specific criteria can be it should have some specific nuclear spins, like lithium, sodium, or fluorine. So these, or nitrogen, you can utilize such a nuclear spins. And actually, on the other hand, we use like relaxometry, so-called. It's a very simple but powerful method, and if we use the dynamics of the molecule, we don't need such specific interactions. So that actually that is interesting, because previously, if you work on the sensing with the MOF, maybe you need to have some very strong interactions, like quenching of the fluorescence or some electronic interactions. But in this case, in the quantum sensing, you can detect the very, very weak interactions, like interaction between electron spin and nuclear spins, dipole-dipole interactions. I think that gives you the different way of sensing. So maybe you can expect that you may have the different response with the molecule with the very similar structure, but they have a very small difference. So you don't need to have the very strong interaction like a previous MOF sensing, but if you use the quantum sensing, maybe you can do the sensing of kind of different family of targets. So it can be, I think it can be the complementary technique with the previous sensing with the MOF and the quantum sensing. Yeah.
I see. Yeah. So basically, the quantum sensing can help to improve the sensitivity, right?
Sensitivity, and also it gives you the chance to enlarge make more variety of the targets you can sense. That doesn't have the strong interactions, electronic interactions, but it can only have the weak interactions. But maybe you can distinguish such weak interactions, because many usually molecules have nuclear spins. So yes, if you can sense the nuclear spin, you can distinguish the molecule like NMR. So quantum sensing can give you such additional feature in terms of the sensing, I think.
I see. Okay. Another question from Grish, and I think this question is more specific towards the chemistry. Very nice talk. How to design conductive MOF for electrochemical application. This is slightly different from today's topic, but any comment on that?
Maybe I'm not the right person to answer that question, but I should mention that in the previous work, like the MOF made by Mitchell Dinka group, they also use the kind of conductive MOF for the quantum sensing, because it can, conductive MOF and it can be used for the electrochemical applications, because by redox reaction, you can make the radical, right? So such a radical can be useful for the quantum sensing. So that can be also interesting application, because many of you already have the very nice MOF. It's can be stable against the chemical reactions or electrochemical reductions or oxidations. So you can produce the radical, you can produce the qubits. So you can even use the same, maybe use the same material for the quantum sensing. And that's a kind of interesting addition to this MOF chemistry community, I think. Yeah.
I see. So before the next question, I want to ask my personal question because I'm very
Yeah.
interested in this topic. Um, when we talk about quantum, we always get an impression that you have to cool down your system to cryogenic conditions to observe any coherence or entanglement, right? But in your case, you have demonstrated even room temperature
Right.
coherence. So I'm
Right.
wondering, what are the conditions that are needed to observe the quantum effect, and how can we make those conditions more user-friendly towards ambient conditions?
Yes. So that's why I mentioned about the bird. In such a, of course, room temperature, and of course, it's in the messy, in the room temperature, very, very friendly situation to our living system. So, but still, you can produce the quantum coherence, and even you can use it. Of course, this is still the hypothesis, but theoretically, it should work. So that's very interesting. So, previously, quantum coherence is made by low temperature because you need to have the long coherence time. For example, for example, computing, it's very severe. So it's quite tough to have very, very long coherence time, like a millisecond or so, to do many computation. That's very tough. So you need a very, very low temperature, very, very isolated superconducting qubits. And so to have a very, very long coherence, very small noise. But for the sensing, you don't need such super long coherence as we see in this example in the natural systems. But actually, instead, but you need to initialize the system. You need to make the first of all quantum coherence or the polarization in the first place. For that, actually, the photo irradiation, as I mentioned, that's a very powerful way. By using the light, even at room temperature, you can make the enough long quantum coherence at room temperature over microseconds. So that is quite enough for some sensing. Of course, longer coherence time should give you the higher sensitivity, but it's long enough. But actually, we can make the coherence only limited time, like microsecond. It's not very long, but we can make such a non-summary equilibrium coherence only short time, but that is actually long enough for the quantum sensing applications. So that is one way of making user friendly or sensing friendly way of making quantum coherence is using the photo excited state, I think. And also, as I mentioned, photo excitation can give you the potential of optical detection. If you need a pulse EPL, that's tough, right? It's very expensive.
Yes.
Yes. Yeah, I want Bruker to make it cheaper, but it's expensive. But no, it's not very common. So, but if you can do the optical detection, so that can even more friendly, and also even if you can do the mapping, and also it can give you the much higher sensitivity. So the photo excitation to make the coherence is not only good for making the coherence, but also for the detections eventually. That's still, ongoing, not developed well, but I believe that's going to be very important. Yeah.
Yeah, that's a very good direction. So we have another question from Rajendra, and very nice, interesting talk. Do you measure the mobility of the guest in corporate MOF by any method, and how much mobility is changed after incorporation?
Yeah, thank you very much. So that's also a very important point. So as I mentioned, actually we have, for example, in this case, we have two types of guests. One is our qubit, DAT, and also another is, for example, benzoquinone or benzene toluene and so on. So, okay, so actually we try to observe because we are interested in the mobility of our qubit itself, but we actually we tried like solid-state NMR and other methods, but we couldn't see it because this is a very tiny amount. Because if we introduce more, we can see it, but it's aggregate and it's totally different situation. So we couldn't experimentally observe, but with the help of MD simulation, we considered this mobility is exists lot of mobility or diffusion exists in the empty situation, but with some gas molecules, it's much suppressed. And we also observed the mobility of another gas, like benzoquinone or other gas molecules, but we found some still motions of the benzoquinone. So maybe some of you have questioned like where is DAT or where is gas? But the answer is that not very much well defined, I think. So because still they're moving. So maybe there's some, maybe there's some preferred position, but it's not very static, at least at room temperature. So yeah, that may be the answer to you.
Okay, so before we end, I want to share some of my personal experience because I was very inspired by your last part on the effect of a motion restriction. You
Okay.
demonstrate that if you can restrict the motion of the ligand, you will make the quantum sensing effect more obvious. You also mentioned some optical property, and in our previous studies, we've demonstrated some MOFs with mobile units. We call them molecular rotors. And then we found that when we expose that to different gas molecule, the color will change. And previously we thought it would be the solvent effect. Now it's probably quantum sensing.
Yeah. It can be.
Yeah,
So I think many people I think I think it's so common, like because that the change the mobility by some guest accommodation because it's exposed. So some mobility should be changed, but we usually don't care so much about it. But
yeah,
if you once work on the quantum sensing, it can be a very unique and important parameters you can care more and
yeah, yeah.
if you think that way, maybe you can find even more interesting viewpoints in your material, I think.
Yeah, because there's a concept called AIE, aggregation induced emission. That is
Right,
very
that
close
kind of,
related with this one.
right, exactly, that should
Yeah,
be also play an important role.
yeah. So probably the final question from Junyi, and she's also from my group. So hi, Prof. Yanai. Thank you very much for the presentation. Are there any disorders of the DPY-DAT ligands in the structure of the DAT MOF 123? And can the disorder be considered as a factor influencing T2? Thank you.
Yeah, thank you very much. Yeah, that's also important. And actually, in case of DAT MOF1, we didn't see the very large disorder. But in case of DAT MOF2 and 3, at least we observe a static or dynamic disorder. Maybe it depends on the temperature. So, and then because this DAT MOF1 have the, as I mentioned, the pi stacking, so it's kind of stopped. But this DAT MOF2 and 3 have the freedom to move, or at least have the disorder. And then we consider that at room temperature, maybe it gives them the additional mobility, and that may reduce the T2. So, but if you have some, some co-ligand that stop the motion, you don't want to have too strong interaction between the chromophore, between the qubits. But if it's a co-ligand, it's fine. So it just stops the motion, and it can keep the coherence. So that's what, in that sense, I think your question about the disorder is a very important role, and that can give us a kind of sense that this morph can be useful, or this morph can be not so good. Yeah, something like that. Yeah.
Okay. Can you briefly comment whether this quantum sensing can be used in biomedical application?
Yeah. So that's the kind of one of the ultimate goals, so that since we can distinguish, because there's a potential to distinguish different molecules, so we can expect some very important biomedical applications, like seeing the metabolites, or seeing some many variety of the chemical compounds in the biological systems. So, and for that we need to make the many different type of sensor that can respond to the different type of the chemicals, maybe some specific, some maybe not, but by combination of the different chemical sensors, I expect that we can eventually distinguish or detect some important chemicals in the mixture of the biological system. I think that's the one of the very important the applications of the quantum sensing.
Okay, thank you very much, Nobu. Thank you for being with us and sharing your exciting result with us. We look forward to seeing you in the MOF 2024 in Singapore this summer.
Yeah, thank you very much, Don, and
Yeah.
good. Yeah, looking forward to see you.
Yeah, thank you. So with that, we will end today's webinar. Thank you all for your time.